Hello, ladies and gentlemen, and welcome back. In this video, we're looking at question B2 on our Canadian senior paper from 2018. There's nothing to read here. They just jump right into it with 4 questions here. Question A, determine the positive integer x. The definite article telling me that there's only going to be one answer. For which 1/4 minus 1 over x is equal to 1/6. Well, we could just rearrange the equation. I'll bring the x over to the other side. Actually, you know what? We could even bring the 1/6 over to the other side as well. And then, well, what's 1/4 minus 1/6? Well, get a common denominator of 12. And 3 minus 2 is 1/12. So x is 12. There we go. Short and sweet. Looks like, just a quick glance at the rest of the problem, it looks like we're talking about these so-called Egyptian fractions of the form 1 over an integer. All right, B part. This appears to be the only one that doesn't have fractions, but that's okay. Determine all pairs of positive integers a, b, for which ab minus b plus a minus 1 equals 4. Okay. Well, it's a highly regular looking expression. I do have it copied, right? Yeah. It looks like I can take out a factor of b here. Get a minus 1 plus a minus 1 here. And now I can take out the factors of a minus 1 that I see, and we'll get b plus 1 times a minus 1 needs to be equal to 4. Okay. Now, all pairs of positive integers a, b. Okay. So, b plus a and a minus 1 could be, well, I don't know. I think it might be easier just to sort of make a little table. I'm trying to say that you can't have negative. What we want to do is, clearly b plus 1 is a factor of 4. A minus 1 is a factor of 4 as well. Let's say b is positive. So is b plus 1. So a minus 1 is 4 over b plus 1 is also positive, because a positive number divided by a positive number is positive. B plus 1 and a minus 1 must be positive factors of 4. So we've got some cases. We can have b plus 1 and a minus 1 are both 2. And that would, so 2 times 2 is 4. And then b would be 2 minus 1, a would be 2 plus 1. Well, that works. And if you worry about your algebra, of course, you could plug it into the original expression, a times b, 3, minus b, which would be minus 1, plus a, add on another 3, so now we're up to 5. Subtract 1, you do get 4. We can have b plus 1 is equal to 4, a minus 1 is equal to 1. Or we could have the opposite. Now, if that's the case, b will be 0 and a will be 5. That doesn't work because b is not positive. But over here we can have b is 3 and a is 2, and both of those are positive, so they work as well. So to summarize, ab is either 3, 1 or 2, 3. All right, so that finishes part B quite nicely. C part, determine the number of pairs of positive integers x, y for which 1 over x minus 1 over y, or 1 over x, y, I said x, y, even though it's y, z. Y, z, for which 1 over y minus 1 over z is equal to 1 over 12. Okay. I suspect B will be involved somehow, but let's Let's see what we can do here. Oh, incidentally, we already know unanswer 4 and 6. We saw that in A part. But what can we do? Well, I can multiply all sides by let's say 12x or 12yz. That would seem to work. And then we'll get 12z minus 12y is equal to yz. Of 12z minus y is equal to yz. Okay, so yz must be a factor of 12. That's certainly true. I'm trying to find something to... Oh. If I bring this over to the other side, I can have yz plus 12y minus 12z, and this is looking very similar to this expression, something minus, something plus, but we don't have a constant to work with. So this is almost y minus 12 z plus 12. Except we don't have the 140. The y and the z will work together to make this. The minus 12 and the z will make this part. The plus 12 and the y will be this part. And the minus 12 times 12 would be minus 144, so we add on 144 to stop that. Or I guess we can just say minus 144 is y minus 12, y plus, or not y plus 12, z plus 12. Okay, and then did we want positive integers? We want positive integers, y and z, that work this way. So one factor must be negative. Another must be positive. Otherwise, you're not getting a negative product here. Now, if z is positive, so is z plus 12. So that tells me y minus 12 must be negative. But y is positive. Y minus 12 is negative. So we can rearrange this one and say y is less than 12. So we need y values between 0 and 12. And I guess this one over here we could say y minus 12 has to be greater than negative 12. And that's going to be kind of crucial because there's only so many factors of negative 144. So we can have y minus 12, z plus 12 will be the corresponding positive factor. And then from there we can work out y and z. So we could have negative 1, negative 2, negative 3, all of these are fine, negative 4. Negative 5 is not a factor of 144. Negative 6 is. Not negative 7, negative 8 is, because it's 9 times 16. Negative 9 is, negative 10 isn't, we still don't have a factor of 5. Neither is negative 11, and negative 12 would be too small. Because y would be 0, and you can't have that. And we don't need to go any further, because the y values will just end up being negative. So our z's will be 144, 72, I can't remember what this is off the top of my head. I'm just going to grab my calculator. 144 divided by 3. Oh, it was 48. That's the first thing that popped into my head, but I didn't go with it. 36, because it should be 12 squared divided by 2 squared should be 6 squared. Divided by 6, we should have 24. I know this one will be 12. This should be 16. This is 18. 144 divided by 8. Yeah, 18. Okay, so the y values are 11. Just keep adding 12 to both sides. So 10, 9, 8, 6, 4, 3. And the z values now I need to subtract 12, so that'll be 60. That'll be 12. 4, 6, 24, 36, and 140, so that'd be 132. Alright, so there we go. And you would just package them up quite nice and neat and tell everybody what you found. But those are all possible pairs, y, z. There's 2, 4, 6, 7. All 7 possible pairs. There we go. So, and they wanted to determine the number of pairs rather than just finding the pair. So, okay, the answer is 7. Now, D part. Prove that for every prime number p, there are at least 2 pairs Rs of positive integers for which 1 over r minus 1 over s is equal to 1 over p squared. So I think the same sort of reasoning should work. Right? The exact same work we just sort of put into it. 1 over r minus 1 over s is 1 over p squared. And so multiply p squared by p squared rs. You'll get p squared s minus p squared r is equal to rs. So we can rearrange and say this is rs minus p squared s plus p squared r. I'm going to add and subtract p to the 4. And so we'll bring in p to the 4 over here. Rs minus p squared s plus p squared r minus p to the 4. And this factors as r minus p squared, has to line up with the s, and s plus p squared. All right, simple as that. Now we want positive, I'm pretty sure it's positive integers, but I want to double check. At least 2 pairs of positive integers, fine. Okay. 1 of r minus p squared s plus p squared is negative. P is greater, or s is greater than 0, so s plus p squared is greater than 0. So r minus p squared must be the negative one. Okay. I think it should just work by saying let r minus p squared equal negative 1. Then s plus p squared will have to be the p to the 4. So we'll have p to the 4 minus p squared, which is p squared minus 1, which is at least 3. I mean, if p was as small as possible, it'd be at least 12. So that would work, and then r would be p squared minus 1, which is a product of 2 other positive integers. I'm just trying to make sure it's clear to whoever's marking that I realize these are definitely positive integers and therefore count. We can also let r minus p squared, what's the other possibility? Minus p would work just fine. So r would be p squared minus p. And that would mean s plus p squared, or s plus p squared has to be the remaining factor of p to the 3. So s is p cubed minus p squared. And there we go. So these are at least 2 possible pairs. That wasn't so bad. So rs can at least be what do I want? What was it? P squared minus 1 p to the 4 minus p squared, or p squared minus p cubed minus p squared. And that works. That was not bad at all. I went through it quite quickly because of how well we did C part. Well, there we go, and that's it for question number 2. So all that's left is the last question, the big question, B3. Please do give it a try before watching the next video so we can explore it together. And yeah, I think that's it. Have yourselves a wonderful day. I will see you for B3 next time.